Our last and final talk is Jonathan Rudd from DS Geophysical.
Good morning, and I want to first thank the DMEC organizers for the opportunity to speak to you. As Andrew mentioned, there's a lot of material to cover, and so I will try to just hit on the highlights, I guess, and I'll largely be focusing on ground electrical methods in this talk, as some of those borehole topics have been already covered. So I just wanted to acknowledge my co-authors, Jeremy Barrett from Southern Rock Geophysics in Chile, and Terry Ritchie, who's with GRS in Australia, and Roger Sharp of Quantec Geoscience here in Canada. I'm with a company called DS Geophysical Limited. How do we classify, or how do we sort of characterize advances, and really it's really the goals that we're trying to achieve in the advances? And I've sort of thought about the fact that we really want to increase resolution, we want to improve safety, we want to improve accuracy and increase our depth search. We also want to expand our sort of ability to survey in new and different environments. So environments perhaps that are more resistive than we've been able to survey well in the past, or more conductive. And so I'll focus sort of the discussion around these 5 areas of expansion. So then we can look at, we address these goals, these expanding boundary goals in a number of areas. Equipment is obviously the first one. It's fundamental to all of these. By improving signal to noise, applying larger or denser arrays, perhaps customized arrays, injecting GPS and real-time communication technologies, we can improve in all these areas. Safety, we've seen great improvement in isolation of the risks inherent in this type of survey, adding purpose-built technologies for safety, and strengthening procedures. The full 3D method and the addition of common voltage referencing recently yield dense full azimuth data sets for more resolution and higher accuracy. Time series acquisition opens up a world of signal processing opportunities, especially on data-rich surveys. The monitoring of external noise can add value where tellurics are intense. Inversion is synonymous with interpretation, and these can extend to many dimensions, from 2D to 5D. There's 3 spatial dimensions, temporal dimension, and the spectral that's already been mentioned as well. There remain many opportunities for further expansion of these boundaries in the electrical method. We look forward to hearing about those 10 years from now. So just wanted to take a brief history. Schlumberger was mentioned. They came in actually 100 years after this method was electrical methods were first introduced, but they did an awful lot of work in bringing in the IP method and resistivity method. And you can see they went straight to the oil and gas industry, perhaps a little brighter than all of us are in that sense. So I've done a quick timeline through from the 1940s, but as I mentioned, the first resistivity surveys were done in 1830. They were largely soundings. The first discovery was made in 1835. Borehole surveys were not done until early 1900s. This was the Schlumberger brothers. And the first IP surveys, or routine IP surveys, were in the 40s. I'm not able to keep up with history clearly here. N=1 surveys from the early 1950s. Siegel did a lot of work in the late 50s and certainly added value. Frequency domain was really quite popular during those 50s and 60s era, and products were described in phase angles and percent frequency effects. The different pole-dipole, pole-pole, dipole-dipole arrays were added through the early 1970s. Coal model was introduced late in that decade. And numerical modeling advanced through that time as well, advanced the interpretability of these data sets. N=4 surveys in the early 1980s, N=6 by the end of that decade. Ken Zong, a lot of contributions, as you know. Telluric cancellation was introduced quite early in the early 80s, and it's still an area of research now. Time domain surveys started to increase through the late 80s, early 90s, and they're now dominating the electrical resistivity world. Oldenburg and Lee changed things dramatically when they published their 2D inversion routines. And then 10 years later, the 3D inversion came through. Distributed arrays improved the depth search capabilities dramatically in the late 90s, early 2000s with the MIMDAS system. And EM coupling was tackled in that decade. Full 3D surveys introduced in the mid to late 2000s. And now we're seeing full azimuth surveys with current monitoring. Common voltage referencing has just been introduced. Multi-scale dipoles and really super sampling, very, very large data sets. So I want to talk briefly first about safety, because safety is first. And in this decade, we've seen the introduction of the GGSSA. It now has 37 member companies, and it does a variety of beneficial things. Those are their purposes, to develop guidelines, to serve as an exchange, information exchange center, and to promote safe practices. On the safety side, a lot of these new developments, as we try to push those boundaries, require a close look at safety matters. And on the transmitter side, as Andrew's mentioned, the isolation is important, automation, and automatic shutdown on fault detection. Those are all very important developments. And we're seeing that spread slowly through the transmitter industry. Lightning shunts are new technologies that have been added. They're separate items which can be added to effectively added to survey areas or equipment, and current lockout systems. Transmitter technology, as I just mentioned, the safety aspects, but the push is to higher power and to higher voltage to expand the boundaries, ability to get deeper and into more resistive environments, conductive environments. Higher power takes you so far because it goes with current squared. Perhaps better to attack lower noise because it's linear, but we are sort of focusing on the higher power at this point over the last decade. There are more high voltage systems. There are 4 or 5 systems now that are offering 4 kilovolt to 10 kilovolt performance. Waveform control, more and more systems are taking a look at how and what the quality of their waveform is. And waveform monitoring, as has been mentioned, is becoming much more common as well, both at the transmitter and at the injection point. Timing control is also necessary for a lot of the distributed systems that are out there. So the transmitters have seen a lot of improvements over the last 10 years. State of the art, I guess, would be a system that offers up to 200 kilowatts, 10,000 volts, and well over 100 amps performance. Looking to the sensor technology, it's kind of the poor sister to the transmitter technologies and the receiver technologies in the electrical geophysics space. Not a lot of change in the last 10 years, and I think not a lot of change in the prior 10 years. Porous spots still reflect, I guess, the lowest noise systems. They are prone to breakage, leakage, and they are higher impedance sensors. So they often in practice become more noisy than the other options, the steel rods or plates. So in practice, it's more often to see steel rods or plates in use. They offer low noise at the operating frequencies of electrical surveys. They do drift, but the drift can be handled fairly easily in the processing because it's linear drift. Low contact impedance is an advantage, and they're durable. They don't tend to, they can't dry out, I guess. There are other options out there that are coming in line. I know there's one group that's used buffer amplifiers over the last decade, and some good results from that. Capacitive electrodes are starting to come into use as well. Not widely used at this point, but we expect that to be a growing area as well. Receiver technologies. What is the state of the art? It's a distributed array with time series acquisition, GPS enabled, and with real-time communication for monitoring QC and monitoring operational aspects of the survey. What are our distributed arrays? They're receivers that have anywhere, typically 1 to 6 channels. The trend is to a lower number of channels, so several systems now with single channel receivers, because it provides full flexibility in array design and implementation. Current monitors are in wide use now, or growing use now, I guess. They're really essential for any modern distributed system that collects time series. 1 is good if you have it at the transmitter. 2 is better because it allows you to do leak detection in the differencing of those 2 monitor recordings. Measurement, we can measure time series acquisition. That's becoming standard. I think we've seen really it go from very few providers offering time series acquisition to the point where almost everybody is moving or has moved into that space. There is the introduction of a CVR, common voltage referencing method, which is a different mode of measurement, and I'll describe that a little further later. Processing and interpretation, it really can be described, the processing part of that can be really described as extracting signal. By measuring time series data, you have a host of opportunity to post-process effectively, because every environment is different, as we've heard. You have to have multiple strategies and multiple options for cases where you've got different noise sources, whether it's external noise sources, geologic noise sources. That flexibility needs to be there. And with the larger data volumes that are coming in, we're seeing more and more automation of the data processing. So an example of that is in the top right, where you're extracting, maybe thousands of dipoles for a given current injection. Some of those dipoles are going to be poorly coupled to the current location or the current direction, so they're going to be higher noise, and so we want to extract those. Extracting those manually is a tedious and perhaps less accurate way of doing it, so that process can be automated by looking at those dipoles geometrically and from a predicted noise standpoint. FFTs and wavelets are being used effectively in the processing as well for filtering and the processing of data. Limited use now, I would say, but that is a growing area as well. Telluric cancellation is becoming more and more widely used. In some environments, there's an example on the bottom there from a survey in Chile. The raw data is shown as the blue trace. There's a scalar approach to telluric cancellation shown in green, so improvement, but still quite noisy data. And the red is a full tensor approach to telluric cancellation. So there's multiple methods out there. The usefulness of it is dependent on the nature of the noise and also the process you use in applying it. So in some cases it's very useful, and in some cases it doesn't really add any value. Just a further example, this is a slide that Roger showed on the weekend about the usefulness of time series data. Without time series data, you might end up with a process profile, a decay profile that looks like the top left image there. But if you double back, analyze your noise source, extract your noise source, you can end up with a much more pleasing decay, which is shown on the top right. Another example is shown on the bottom left, where you've got a very clear noise source in there, and with proper analysis in the time series, you can totally remove some of these coherent noise sources. Processing and interpretation. This is the interpretation side, extracting meaning from the data. Inversion has become synonymous with interpretation. These run from 2D to 3D. I think we have heard a lot about these. 4D is the time-lapse approach, and the 5D would be the spectral component. We're seeing joint inversion of these data sets with MT and 2D IP and resistivity 2D resistivity surveys. So an effective integration of different data sets. But the real test is what you do after the inversion. Inversion really just produces images from which the true interpretation of the geophysics and derived geology is then based. And that integration piece was experienced by the oil and gas industry in the 90s. And this is Amoco's experience with the introduction of 3D seismic to their toolkit. And in the mid-90s, 93 to 94, was the time when they recognized that they really did have to properly integrate the 3D seismic results before they started to see the real value and effective use of those data sets towards success in their drilling. So we think that is still to be learned in the 3D IP and resistivity space. So I have 3 examples to show of surveys that have been completed. This is an example that was surveyed for first quantum minerals in South America, over the Atlántida deposit. It was a feature that was explored largely for a skarn mineralization that was at surface, and wasn't really recognized as a porphyry target until later when Inmet came in and drilled some of the IP responses from an old survey and started to hit mineralization. First Quantum came in, took over the project, and did an IP resistivity and MT survey. This example shows the layout of 1 kilometer spaced, so fairly regional reconnaissance IP resistivity and MT surveys, and then a single line of data you can see as the red dots. Multiple transmits to allow for more robust interpretation of the IP and resistivity data sets. So this is a view of the 2D line that was surveyed. These are the inversion products for the resistivity in the top and the chargeability in the bottom. We can see the chargeable response identifying the porphyry system at depth. This is the 1 by 1 kilometer grid of the vector IP data across the survey area, obviously identifying in a very basic sort of a gradient style display here, a 2D style display here, the mineralization. But then when you invert that in 3D using the multiple transmit points, it's a relatively sparse 3D inversion, I guess you could say, but it was effective in mapping the resistivity and the chargeable sources related to the porphyry mineralization at depth. Very large survey area and an effective modeling. This is the MT result that came from the same setups through the survey area. Second example is an example that was also from Chile, a porphyry target. Cerro del Medio, the client is Cerro Grande Exploration. This is a survey done by the Orion system of Quantec Geoscience. And a description, a fairly complex porphyry system with various styles of alteration and the mineralization that you might expect from that. It's an 8 kilometer by 3 kilometer survey area, so still quite large, but certainly smaller scale than the reconnaissance survey that I just showed you. The survey was occupied by 300 receiver dipoles at 150 meter spacing. Of interest, there's a gap in the survey area through the southern section here. There was an access limitation. Local, I guess, landowners wouldn't let the crew on site, but that didn't really bother the survey. You can bridge over these with the distributed array system. You can bridge over these types of gaps fairly effectively and get coverage beneath it. The result is not coming up. There it is. So, 150,000 IP data records collected as part of this survey. You can start to do your interpretation. But the real value comes out when you do the 3D inversion. This inversion senses down from a range of 300 meters down to about a kilometer depth in the center. The depth is aided by the fact that it's draped over a mountain, but still good depth penetration. The IP model result, you can see the annulus of pyrite alteration around the core. And you can see the core mineralization as in that slice. The top right is the resistivity, is the resistivity result. MT was also added to this survey, and you can see the MT data set provides imaging of the core, the conductive core of this feature, but also potential piping source. Third example is from Canada. It's over a uranium, unconformity uranium deposit. So the intent of the survey was to map the map the resistivity signature over this deposit. The mineralization itself is not expected to be chargeable or conductive, but the alteration associated with it was hoped to be detected. So a relatively small survey area of 1.5 by 1.5 kilometers, and over this deposit, which extends from about 100 meters depth down to about 700 meters depth. The deposit is comprised of a series of lenses, mineralized shear zones, and the heart of the mineralization is at about a 350 to 450 meter depth. That's the darker colored high-grade domain. The survey layout was a hybrid approach where we had 60 meter along strike spacing, 120 meter cross-line spacing. We added electrodes near the transmitter injection point to increase resolution, and we injected about 1,000 current injection points. We had 220 active receivers per injection for a total of 240,000 data records. But because of the CVR approach to surveying, we were actually able to extract up to 26.5 million data points. We didn't do that, but that's the available data set from this survey. So to let you know a little bit about the common voltage reference, most surveys will take a channel of acquisition and apply it to a dipole. So you're measuring one channel per dipole. With the CVR approach, you're putting a receiver at each electrode. And then you subtract the response in the time series between those two electrodes. The advantage of that is when you grow your array, you can then subtract any two electrodes, whether it's an adjacent electrode or not. Another advantage is that you're subtracting any induced noise that's in the wire itself, because that noise is going to be common to each of the receiver responses. So you get a low noise and more flexibility in your dipole selection. So for a 6x6 receiver array, you can construct a vast number of dipoles in this fashion. And this button is not moving very fast. So for this survey area, this is an example of the monitoring that's capable with modern systems. We have the ability to monitor each of those receivers. These receivers are actually colored based on the primary voltage, so that's requested. It can also be colored based on the battery life or any other parameter that's important to the survey. So we can see the VP, So the VP is where the dark blue color is, and it's falling away to the orangish colors away from that injection point. This is the final data set from this survey. It's about 1.1 million data points that was fed into a 3D inversion. This particular inversion was done with the UBC GIF code. And you can see this is the observed minus the predicted resistivity point cloud. The result from this particular survey, this is a plan view, was quite pleasing to the client. There was a very, very strong correlation between the mineralization, which I'll actually bring up now, if it'll come, which sits there, and a very conductive response, which is peripheral to the mineralization. And it correlated well with their known alteration system in the bedrock. So that most conductive portion of the response is down at 350 to 450 meters down, and correlates with their highest, with their best uranium mineralization. Of course, the eye is drawn to this other response down in the southwest here. Very similar characteristics, a little bit closer to surface, And so they drilled that target, and they've discovered another zone, very similar in character, both alteration and mineralization, 400 meters to the south of the existing mineralization. So just a geophysical discovery, which is always nice to see. I think I'm out of time. I'm out of time, so we won't go over this, but I do want to just mention a few comments on outlook. We do anticipate improvement in the sensor technologies. We do anticipate a growth in the number and styles of arrays that are available, and more custom arrays. The QC automation of the QC of these large data sets. I wanted to sort of highlight this comment about better informed inversions. As we get these larger data sets, we're beginning to understand that the data that you put to the inversion will really sort of determine what your inversion is focusing on. So a larger dipole input into an inversion will focus at depth. A smaller dipole input to an inversion will focus in the near surface. So we're learning that, and we believe there's going to be a lot of work in understanding how best to inform 3D inversions with these large data sets. There will be subsets of the total data set for efficiency of processing time, but we have to be smart in how we select what data to invert. So with that, I'll thank you for your attention.